Okay, this is the review video that's going to cover the problems from chapter 2, 3, and 7 that I want you to know for the final exam. And the purpose of this video is just to review, like I said, but let me go ahead and remind you that the final exam is going to be on, when is it? May 3rd at 10:30 a.m. It's going to be given remotely, meaning that you will take it at your computer or laptop at home or in your dorm or wherever, your apartment, wherever, or at the library if you need to. So we will not be meeting to take the exam. You'll take it through something called HonorLock, which hopefully most of you will know about. It's basically a browser extension that you download into Google Chrome, and it monitors your progress through your webcam, and it monitors your web activity. So you will need a computer with a webcam. You're going to need your student ID to take it as well, because it's going to want to see your student ID to make sure that you are the person that you say you are, and that you're not having someone else take the exam for you. I'll give you guys more detailed info about how exactly to open the exam through HonorLock in either a separate video or just via our normal Teams meetings. Okay, so here we go. This is going to be the first question, coming from, just going in order, this is from chapter 2, which was the set theory stuff. So in chapter 2, we first started talking about what a set was, and then we talked about different set operations like unions and intersections. Remember the capital U looking thing and then the upside down capital U. We looked at complements of sets. We looked at what else did we look at? Power sets. Did we look at power sets? What else did we look at? Universal sets, the empty set, De Morgan's laws, and then we got into the section involving Venn diagrams, which is what I would like you to be familiar with. And then in the last section of chapter 2, we did survey analysis, which basically means like analyzing data given from a survey using Venn diagrams, and that's when we got into those Venn diagrams that can involve 3 sets, right? This is not one of those, right? Talking about the kind with 3 circles, 3 sets represented by circles. Okay, but the problem I'd like you to do here is, given a Venn diagram of this form, so 2 sets, with data being outside of the 2 sets, so in all of these names, all of these 12 names, 12 names are in the universal set U, right? So what is that universal set? It's the set of students in a class. So this rectangle represents the class. Then they've been further classified into sets A and B. A is students who play hockey. So these 5 students over here play hockey. Max, Lisa, Sam, Mia, and Ty. Set B is the set of students who play basketball. So we've got 8 students who play basketball. Sam, Mia, Ty, Dan, Tim, Jill, and Jack. And then we have 3 out here who don't play either of these sports. Maybe they don't play any sports, or maybe they play a different sport. We don't know. But they are in the class. And all of these students are still in the class, right? They're all in the universal set. It's just that these have been further classified, further organized into sets A and B. And then we have these 3 students here who play hockey and basketball. So the first question here says, determine which students only play basketball. Determine which students only play basketball. So I would say only basketball. Well, B is the set of students who play basketball, so these 8 students play basketball, but I want to know the students who only play basketball. Well, that would be not these 3 that also play hockey. So only Dan, Tim, Jill, and Jack. Okay. Second question, determine which students play neither sport. So neither hockey nor basketball. And that would be the students who are not organized into sets A or B, right? They're outside of both of those. So that would be Bob, Joe, and Kate. Determine which students play both sports. That's going to be the intersection right in the middle there. Sam, Mia, that's Sam, I just wrote it weird. Mia and Ty. There we go. That's it. These are very intuitive, right? These two set Venn diagrams are very intuitive. The only tricky things are to recall that all of these are still in the class, right? Just because like Max and Lisa, Sam, Mia, and Ty are in set A, it doesn't mean they're not also in U, right? Because these two sets, A and B, both completely live inside the set U. Right, so all 12, right, it was 12, I believe. All 12 of these students all live in this set U because U is the set of students in the whole class, right? So that's one tricky thing to remember. But other than that, I feel like most of this is pretty intuitive. Just make sure you don't get the set names mixed up, right? If it says B is a set of students who play basketball, determine which students only play basketball, just make sure you're looking at the right set, right? The B set. And then you want to make sure that you exclude, for that first question, you're excluding the overlap with the set A. And that's why I only wrote these 4. Okay. Chapter 3 was logic, what was it? What was the actual name? It was logic theory, basically. So we talked about logical statements. We had some really technical definitions for, or very precise definitions for what a mathematical statement technically is. And then the major thing though was looking at the different types of compound statements, like if-then statements like this, denoted by this little double-sided arrow, and statements like this. And then or statements like this. So recall that and statements we use the fancy word conjunction, and then or statements were disjunctions. And then we called these conditionals. Okay, and they all had their own truth table. So these problems, when I'm not showing you explicitly the truth table for an and statement. You notice these are all a little bit more complicated, slightly, because they have a little negation. That little squiggly line, remember, that's a negation. So when you're reviewing for this, you also need to make sure you know the base tables for just your, you need to know how the and works. So you should recall how those work, how the ors, and I'll just use C and D for all the letters here, and how the conditional works. Just a basic truth table for each of those with no negations, no extra stuff attached. And this will be, these will be in the book or in your notes. Or you could look them up online too, because this stuff's pretty common. Okay, so here though, we're going to, in these are 3 separate problems here. Going a little bit further, introducing a negation, just to complicate things a little bit. Okay, so the first thing that's already done in this problem is the base to the 4 possible combinations of truth, either true or false, have already been listed for our 2 variables in all of these. So I've got true, 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 false, false, true, false, false. That's every combination that's possible given 2 variables. And you see that's why all of these are the same size, because it's just 2 variables in each of these examples. So that's already been done for us. That's not really part of the problem anyways, that's just setting it up. Where the work starts is when you're figuring out each piece of the statement here, and then the whole thing. So first, when I want to negate D, that means I look at the D column and I literally take the opposite. Okay, literally taking the opposite. So instead of true, it's false. Instead of false, it's true. Instead of true, it's false. Instead of false, it's true. Okay, now I want to look at connecting this column with this column now, because now I have that piece, C and negation of D. And I'm saying and because that's what that symbol means. That's an and. So I need to recall that the rule for an and is that it's only true when both pieces are true. So that means here I've got true and false. Well, that ends up being false. It's only true when both pieces are true. Both pieces being the pieces coming from each of these columns here. So in the second one I have true and true. That yields true. And then false and false, that's definitely false. And then false true, that's false. Only way it's true is if both pieces are true. And notice I'm using the negation of D column. Right? That's why I'm purposely blocking out the D column here so we don't get mixed up, right? So we don't accidentally look at the D column. We want to cover that up because we're supposed to connect C with the negation of D. Okay, so that's why I'm looking specifically at these two columns here. So I have to know what columns I'm looking at, right? Be careful of that, and also know how that little connecting piece, the and, what the rule for it is. And the rule for the and is that it's only going to yield a true when both pieces are true. All right. Let's go to this one. So I want to first it's an or statement. So in the last column I'll need to recall what the rule is for or. Right. First though I need to negate A. So I'm going to look at the A column and negate that. So literally opposite. So I'm just flipping true to false, false to true, false to true. Okay. And now I'm going to want to cover up the A column because I want to connect the negation of A with B via an or. And the rule for or is it's only false when both pieces are false. It's like almost like completely opposite from the and, right? It's for an or statement, which is this symbol, they're only false when both pieces are false. So that means this is true, this one is false because both pieces are false, this one is true, and this one is true. Only false when both pieces are false and the rest are true. Then you have your conditional here, the if-then. So again, before I even remember the rule for the if-then, I need to go ahead and negate Q. So I'm going to take the negation of Q here, flipping all of those, and then I'll cover that up. Okay, and now I want to think of if P, then negation of Q. So if this, then this. If this, then this. Remember, the order matters for these conditionals. You have to make sure you're going in the right order. It's not really a problem in this particular setup because in the top you're reading it from left to right, and down here they're in the same order. They're still reading from left to right. So no issues there. But just remember that things can get like what if I wrote Q implies not P or something like that. Then you would have to be really careful about reading your truth table backwards, and that can get, it can get a little, it's easy to get mixed up, so just be careful of that. Not as big of an issue in this problem though, because it's going in the same order. Now what's the rule for conditionals? If P, then Q. Oops. The rule was that it's only false when you have the combination of true, false. So remember, those were a bit weird. You're going to have to go back and think about how those worked again, and maybe you figured it out back then, but it fell out of your brain since then. You're going to have to refigure that out because it's very not intuitive. But we spent a bit of time talking about why when your first variable here, the so-called antecedent whatever. We don't need to know the technical. In fact, I don't even know if that's right. What is it called? The hypothesis. Anyways, if the first part here is false, it's just automatically true. We say it's vacuously true because it's almost like a meaningless statement, and it's just technically true, right? So we spent a lot. I don't want to rehash that whole discussion because we spent a fair bit of time talking about that. The combinations that start with a false. You're just gonna have to go study and review that. But basically, the rule is it's only false when you get the combo in the order true, false. So that means this one is false, true, true, true. Only false when it's true, false. In that order, true, false yields false. Okay. Okay. Alright, what is next? So that was logic and sets and logic, and then so the chapter 4, the ratios, rates, and proportions and percentages, you're seeing that that's not appearing here, and that's because the math that you have to do in there, especially the percentages, you're already responsible for in chapter 9 in this 9.1, the simple interest stuff. Or was it even 9.1? Well, the sale price stuff, sale price and taxes and all that, you're already having to deal with percentages there, so I trust that chapter in that section in particular is going to tell me that you know how to deal with percentages. And then there's also geometry, chapter 6, but I mean, I just wanted to cut something, and geometry didn't make the final cut for the final exam, so no need to worry about geometry, at least for the exam. So we come to the last thing to review here, which is probability. And these are very, very simple probability problems, and I've got 3 of them here. And in fact, I wanted to go over some almost too simple probability questions just to make sure that you have a good idea about these like special cases when probability is equal to 0 and when it's equal to 1. In other words, when something is impossible versus something that is definitely going to happen. Those 2 extreme cases, because I don't think we really talked about those that much explicitly. So let's see what we got here. A standard die is rolled. So when it says standard die, that means like a 6-sided die. So 6 sides to the dice, or to the die, and then find each probability. The first one says the number rolled is less than 1. So think about that. You roll a die, sorry, the singular is die. What is the probability that it's going to be less than 1? Well, that's impossible, right? Because the lowest number is a 1. You can't roll anything less than 1. So I'm going to say, since this is impossible, the probability, how do we measure that then with a number? The probability is 0. That's how we measure it. 0 chance that that would happen. All right. Part 2. What is the, so now here's the opposite extreme case. The number rolled is less than 10. Well, the numbers are 1, 2, 3, 4, 5, or 6 for a standard die. So what are the chances that the number is going to be less than 10? Well, 100%, right? So in other words, I'll say it like this. Since this is definitely going to happen, guaranteed, right? Guaranteed it's going to happen. How do we say 100%? What is 100% as a decimal number? 1. Remember, all of our probability should always, in any case, probability measures from 0 to 1, always. The lowest probability you can ever have is 0, and the highest probability you can ever have is 1. So these are like the extreme ends of the spectrum cases, right? But we can still talk about them. We can still ask questions like this. They're kind of meaningless questions, really, because, I don't know, they're not that particularly interesting. But anyways, they can still be asked. So here's number 3, I'll write over here. The number rolled is less than or equal to 3. So that's interesting. Finally, an interesting one. So, oof. The number rolled is less than or equal to 3. So what numbers are less than or equal to 3? 3, 2, and 1. At least in this rolling a die, right? The 3 numbers that are less than or equal to 3 are going to be 3, 2, or 1. Okay. So how do we say that? Well, so my probability fraction, probability of this event, E, which E is rolling a number less than or equal to 3. So remember that I'm using the capital letter E to represent that, but you could literally write that sentence in the parentheses, rolling a number less than or equal to 3, close parentheses. But I'm just being lazy and just calling it capital E for just generically, like for event. Okay, and I'm going to have the size excuse me, the size of my event space over the size of my sample space. So what's happening up here is I have the numbers less than or equal to 3 in a setup here. Well, so I think when we did these before, I used a bit more space, and I wrote like size of event space, and I wrote that off on the side, and I wrote size of sample space, and I wrote that off on the side, and then I put the numbers up in the numerator and the denominator, respectively. So I think I'm going to do that now instead of, I was going to write the set here with those numbers in there, but I don't want to confuse you with like doing it a different way for the review. So I'm a little squished here, so let me just talk about what I'm going to do here instead of writing it all down. Okay, so in the top, I want to have this situation represented. How many things can happen? How many times? How many numbers can you roll where it's less than or equal to 3? Well, 3, 2, or 1. That's 3 numbers. Okay. How many possible rolls can you get? 6, right? Because it's a standard die. So 3 out of 6 is 1/2. Technically, what's happening though is that 3 represents the size of the event space, and the 6 represents the size of the sample space. Okay, where the event space is the things that are happening that we're trying to measure, that less than or equal to 3, and the sample space is the every possibility that's possible in the experiment, which would be, in this case, rolling a standard 6-sided die. That's why it's 6, because there are 6 possible options. Alright. A card is drawn. New problem. A card is drawn from a standard deck of 52 cards. Find each probability. The card is neither red nor black. Well, if this is a standard deck of cards, then all the cards are one of those. They're either, if you draw a card, it's either going to be red or black, right? If it's a standard deck, right? Not some fancy deck, so it's just a normal deck of cards. Then this is impossible for neither card to be red or black. So it's just like part 1 up here, the probability is 0 because it's impossible. What about the probability of the card being red? Well, how many of the cards are red? So I'm just going to use a generic E here again for probability of the event. When you draw a card, what's the size of the event space if you want the card to be red, or if you're measuring how likely it is for the card to be red? Well, half of them are red, so that's 26. Okay. And what is the size of the sample space if you randomly pull a card from a whole deck of 52 cards? Well, it's 52. Okay, and that's going to be 1/2, or 50%, if you like that better as a percentage. This is probably the safest way to write it, though. Nice clean fraction. Okay, so you can tell I'm not trying to get you to do any fancy probabilities. No counting techniques needed like we did in 7.2 and 0.3. These are just, do you know what a probability is, right? That's basically, you know, what these questions are getting at. Okay, 2 coins are flipped. Find each probability. 2 coins, so you're flipping 2 coins now. What is the probability of getting 2 heads? So the probability of event being getting 2 heads, well, how many ways, if you flip 2 coins, how many different ways are there to get 2 heads? Well, there's only going to be one way, right? Like, think about every possibility. You can have heads, heads. You can have heads, tails. You could have tails, heads, if you consider that to be different, which we do. And then, because let's pretend like the 2 coins, they're easy to tell apart, you know, so tails, heads, heads, tails, and then the last combo would be tails, tails, right? So there's only one way to get 2 heads. So only one way that can happen, and that's if they both land on heads. But how many different possibilities are there altogether? Well, I just laid them all out, right? It's 4, so that's 1/4. There we go, 1/4, or 0.25, or 25%. So if you wanted to write out this a little bit better here, for every combination, you could say heads, heads. So if this would be my sample space, and this would be me listing my sample space. Heads, tails, tails, heads, or tails, tails. And then, so that's my sample space, and what's the size of it? 4, right? What's my event space? Well, heads, heads. How many, what's the size of this? Only 1, right? There's only 1 element in here. And that goes up here. 1/4. Okay, what about part 2 here? Both coins land on neither heads nor tails. Well, that doesn't make sense, right? It's like, what does that mean? They land straight up and down? Come on, that's, you know, maybe there is like a microscopic chance that that happens, but we will say no. P of E, or I'll just say it in words here, probability is 0. All these that I've said are these special cases, like probability is 0, you can still write it like probability of event is equal to 0. You can still write it that way. Same with part 2 up here where I said the probability is 1. Well, I can still write it, you know, in that form, like that. It's just, since it's such a special case, it almost feels like it warrants writing a bit more of an answer, like in words. But you can still just say, you don't have to write it in words, you can just say P equals 0, you know, or P of E equals 0. Alright. So we did go a lot further with probability than this. In fact, this was like really like day 1 probability stuff for us, because we talked about counting methods, factorials, combinations, permutations, a lot of interesting stuff. But and then we did probabilities with them. That was kind of the point of learning those counting techniques. But in this, I just need you to know basic probability, how to calculate these basic probabilities, and also knowing those extreme cases when the probability is 0 or 1. So that's going to be it. That is the whole review video. Alright. You can let me know if you have questions about this by posting in the discussion chat below, or just email me or send me a chat in Teams.